let's get started on 14. Chemical equilibrium. The fact of the matter is, in the kinetics chapter, we just talked about reactants becoming products, right? This reactant getting used up as the products are being formed. But in the real world, the reverse reaction can occur. And a lot of times, reactions don't even make it to fully products. We end up with a mixture of reactants and products after it's been left to settle and do what it does. So this is a very simple equilibrium right here. The N2O4 is a molecule that breaks up. It breaks apart into two NO2 molecules. And we have equilibrium arrows now. So make sure that you draw these correctly. This is not a double head, not a single double-headed arrow. Okay? It's two single-barbed arrows like that that shows that the forward reaction and the reverse reaction are happening simultaneously. So let's do just a little thought experiment with this N2O4. Let's say we start with pure N2O4 in a container. Okay? Say we have a way of making it or whatever. Okay? N2O4, okay, our container is just that, none of this product there. Okay? The forward rate, when we talk about forward rate and reverse rate, we're talking about the rate of the forward reaction and the reverse reaction. Okay? So that forward rate starts fast. Because if all we're starting with is N2O4, then we have no choice. The only possible thing that can happen is converting it into product. Okay? What about the reverse rate at time 0? Yeah, 0. Reverse rate. No NO2 initially. Okay. Can't have any reverse rate if we have nothing to make it from, right? As more product is formed, what happens to each rate? What do you suppose happens to the forward rate? It decreases as N2O4 is consumed. As we have less and less of that N2O4, okay, we have less and less of that forward reaction happening. Okay? So what's going to happen to the reverse rate? If it starts at 0, it has nowhere to go, but it increases. But it increases as NO2 is formed. All right? You see where we're going here. Eventually, both of those rates will be. Okay? And we defined dynamic equilibrium before when we have two opposite processes occurring at the same rate. Okay? That's when forward and reverse rates are equal. Technically for us, we'll always be referring to dynamic equilibrium. That's when you have two actual processes happening that are doing opposite things at the same rate. Okay? We will just call it equilibrium from now on, but we have to specify dynamic equilibrium. There's static equilibrium, dealing with how weights are distributed on a seesaw or something like that, but that's not what we're talking about. So forward and reverse rates are equal. So let's draw some graphs. Let's have a graph of concentration versus time. Let's have a graph of rate versus time. we've got N2O4 and NO2. At time 0, where should my concentration of N2O4 be? What do you think? Somewhere 0? If we are pretending that yeah, it's this. Imagine we start with pure N2O4 in a container. So if we're starting out, we're going to have some starting concentration of N2O4, and then the NO2 would be what? Initially 0. Okay. Zero. All right. So we said that the forward rate starts fast for removing NO2. Okay? So that means its concentration is going to drop fast to start with. Right? But then we said the forward rate decreases. What's that going to mean about how that line is going to be shaped if the rate is decreasing? It's going to, it's going to flatten out, right? So draw something like that. Oops. There. So actually do something like that. Have it actually be flattening out at some point. Okay? NO2 will be the opposite. Now, I'm not going to have these meet because they don't have to. I'm just going to do something like that.
If you had like excess of the reactant, and there was like two reactants, would that be why they wouldn't meet like that?
We're going to have a whole conversation about where these lines are, but it could be anywhere. Yeah. I mean, this one could be up above or whatever. It's just they're probably not together. Okay? But what's important is that they've flattened out at a certain point, maybe like that. And then, or at least they're supposed to, but that's when we're at equilibrium. Okay. Close enough, right? Make a little arrow there to show that that'll continue like that. Okay. Rates. It's going to be similar, except on this graph of rates. Go to the middle here, and these graphs actually meet. Something like that. So here's the forward reaction. Here's the reverse reaction. Here's when they're at equilibrium. Okay? So rate's the same. Rates are the same. Okay? Concentrations are not the same, but how could we describe what's happened to the concentrations at equilibrium? How would you describe that?
They become constant.
Yeah, concentrations become constant. So that works. Concentrations stop changing. Okay. That's not because the reaction stops, but it's because every time a forward reaction happens, a reverse reaction also happens because they're going at the same rate at that point. Okay. One way of thinking of it is two rooms separated by revolving door. Just draw a little picture right here. There's our revolving door. And you could have a whole lot of people in this room, right? And fewer people in this room, but you could still imagine those amounts staying the same if for every one person that went in that way, one person also went in that way. Right? So if you had people sort of paired up so that one person entered that revolving door from each side, the concentrations or the amounts on each side would remain constant, but they don't have to be the same in order for that to happen. Okay? So that's a common misconception, that the reactant and product have to be the same. They don't. We could have a lot of reactant in a little product, but what's happened at equilibrium is that the rates of conversion are equal, okay, going back and forth. That makes sense? So look at these examples. Okay? These are concentrations. Okay? So here we just said that. How would you complete that sentence? The system is at equilibrium. The concentrations of reactants and products are constant. Not changing. Okay. So here's an example. HI is the product. Okay. Start out with none of it. We make HI. We consume both of those reactants. We could have the reactants present in different amounts, right? Looks like we have an excess of H2, okay, in there. But it doesn't matter. We don't use up all of the limiting reactant. Okay? In limiting reactant really only applies when the reaction goes fully to completion, but that rarely happens. So here's an example where at equilibrium we have fairly low concentrations of H2 and I2, and a fairly high concentration of HI, but it's not complete and total. It's just the concentrations have stopped, okay, at that point. So what's kind of interesting, and I think what is useful for us to consider, is that in this part of the graph, that's what we studied last chapter. Okay? When the reaction starts and how the concentration changes, just sort of from the start. Okay? This is the kinetic control. Meaning if we heat it up or cool it down, we'll change the slopes of these, right? We'll make the reaction go faster or slower, okay? But ultimately, it's going to end up over here. This is equilibrium. So all reactions will reach equilibrium eventually, okay? Kinetics is just talking about how fast we get there, right? So last chapter, we were just really focusing on really the beginning, okay? Right? Sort of the instant the reaction starts and what happens sort of shortly after that, okay? In this chapter, we're talking about the end, where it settles at, okay? What you're left with after you've left it to do its thing and now nothing is changing anymore. It's sort of settled into its kind of natural state, okay? That's determined by equilibrium. Okay? So very often, and we'll talk a little bit about this at the end of this chapter, very often you have to look at both of these because sometimes one will change the other. Okay? There are times when you want to speed a reaction up, but that may screw up the equilibrium and you may be producing less product that you want. Or you may be doing something to get as much product as you want, but maybe that'll make the reaction too slow to do. So both of those are things that you have to consider. So let's talk about a way that we can quantify some of this. The equilibrium constant, which, just to make things super user-friendly, is also a K, but it's a capital K. I want another K for you guys. K ends up probably being the most used letter in, in this entire chapter. Remember, there was Henry's law constants. There were the freezing and melting constants. Those were all K's. So, just a regular lowercase k is a rate constant. Capital K is an equilibrium constant. Okay? And they mean different things, but you got to get used to it. So, ratio of product to reactant concentrations at equilibrium. That's it. So, it's products over reactants. At equilibrium. Okay? So, here's a general equation. The capital letters are the substances, and the little letters in front are their coefficients. So we get to actually make predictions now based on those coefficients. It's going to be a fraction. The equilibrium constant is a fraction. Okay. It's going to be concentrations of what on top? Products. So I got C and D, and those are going to be raised to their coefficients. So A, little a, B, little b. Okay? But these are concentrations at equilibrium. That's important. Because those concentrations could be anything. During the kinetic portion of the reaction, those concentrations were sort of all over the place. But only once they've become constant at equilibrium, that's when the equilibrium constant is. So, unlike a rate constant, we can predict equilibrium constants just from the balanced equation. Okay? And that's because everything has settled out. It doesn't matter what steps happened. Okay? We just have concentrations here, okay? And that's it. It's stopped. Kinetics depended on what step happened, which was the slow one, what was the sequence, all that sort of stuff. So kinetics you can't figure out. So let's just write these ones quick. What's going to be the top of the fraction for this one? Yep, concentration of NO2 squared over N2O4. Okay. For this one, what's it going to be? Okay. H2 concentration times I2. Okay. I'm just going to write EQ next to those just as a reminder. Okay. Let's make some sense of this. What does that very generally mean if K is greater than 1? In any of those cases, what's the general thing we could say if K happens to be a number that's greater than 1? Higher concentration of product at equilibrium. Less than 1. reactants favored. That's the term we're going to use. Okay. So look at that graph up above here. Does this have a equilibrium constant greater than 1 or less than 1? Greater than 1, right? HI is the product. Okay, as it's written there, H2 plus I2 make 2HI. Got a high concentration of that. It's going to be that same one that we wrote down there, but then K is going to be greater than 1. Product favored at equilibrium. That look good? All right, so we will get into doing the actual calculations with equilibrium constants next time, which will be nice because that'll make our lab actually go a lot smoother. So we'll be doing that. Yeah, because of this week from today. All right, have a nice weekend.